Hi ladies and gentlemen, it's Mr. Green again, and this is another in my series of videos for AP Statistics. Today we're going to be looking at the concept of a least squared line. Okay? So what are we doing? We're finding the least squared line that will actually predict values for us. So what are we doing? We're taking bivariate data. We've got an x, a variable that is the independent or explanatory variable, a y variable, which is the dependent or the response variable, and we're trying to use x to predict the value of y. So what are we going to do? If we do a least squared regression analysis, what we wind up with is this equation, y hat equals a plus bx. The y hat means it is the predicted y, not the actual y, but the predicted y. The b in this situation is the slope. It is the approximate amount by which y increases when x increases by 1 unit. A, that's the y-intercept. It is the approximate height of the line when x is equal to 0. In some situations, the y-intercept just means nothing whatsoever, but you use it in a linear equation, and so we're going to make certain it's in here so that you understand what's going on. Now, I want to caution you. Always remember to put that hat on the y here, okay? Why? Because we're not talking about the actual y that we have in our data. We're not talking about that data, that number. We're talking about a predicted y, and therefore it's a different y, and you got to make certain you distinguish it, and the way you distinguish it is by putting that hat on top of it. So, least square regression line. It is the line that gives the best fit to the data set that we have. It's the line that minimizes the sum of the squares of the deviations from that line. Now, let me explain both those two things by going through and giving you several examples here. If we're looking at three data points here, 0, 0, 310, and 6, 2, and we key those into our calculator, we get a regression line that looks like this, okay? 0.5 plus 4. Well, is that the least squared regression line? Let's look at it. If we take the y hat using this equation and calculate y hat for 0, 0 times 0.5 gives me 0 plus 4 gives me a 4. And then I take the actual value, 0, and I subtract the 4 from it, I get a negative 4. If I do the same thing here for 3, put 3 in for x, 0.5 times 3 plus 4 gives me 5.5. I take the actual value, 10, minus the 5.5, I have a 4.5. If I do the same thing for this value here, 6, 1/2 of 6, 3 plus 4, 7. So 2, which was the actual value that we have, minus the 7 gives me a negative 5. If I take negative 4 squared, 16, plus negative 5 squared, 25, and add it to the square of 4.5, I'm going to get 61.25. That is the sum of the squares. So is this line the best line I could use for that? Well, look at this one. If I do the same thing finding this one and then find the y minus y hat, I come up with a sum of squares of 54. So which one of these would be the one that has the lowest sum of squares? It'd be this one here that has 54. This would be the better line to come up with. This would be my least squared regression line, the 1/3 x plus 3. Okay? And we could do the same thing with this. Stick a 0 in for the x. 0 times 1/3, 0 plus 3. That gives me a 3. Okay? Stick a 3 in for the x. 3 times 1/3 gives me a 2. 2 plus 3 is 5. 10 minus 5 is a... not 6. Stick a 3 in that. It's 1. 1 plus 3 is 4. 10 minus 4 is a 6. Golly, Charles. Check your math. Okay. Stick a 6 in here. 6 times 1/3 is a 2. 2 plus 3 is a 5. 2 minus 5 gives me a -3. And then I take these values, 3, -3, -3. That's 9 and 9 and 36. That's where I got the 54. Okay? So remember, we're trying to find the line that minimizes the sum of the squares of the deviations from the line. This becomes my least squared uh, regression line. This becomes my least squared regression line. This becomes my sum of squares. That's my line that I would be looking for. Okay? So how did I do this on the calculator? I think that if you go back and watch and look at what we do in the lessons, they actually show you how to do this. But what I'm doing here is I'm pressing Stat, and I'm going over to Calc, and then number 8 is a least square analysis, and I can stick two lists in there, L1, L2, or second L1, second L2. Oops, didn't want to do that. So I got L1 there, and I do second L2, and I do a regression on it by pressing enter, 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 and hit enter on that, and it gives me the regression on it. Okay? This would be my line of least resistance here. So A is 198.7. B is a negative 7.6. Or negative 0.76. That's what's going in there. That's where I'm getting that regression line. That's what we're talking about doing, is finding that best fit line. Okay? So let's look at some interpretations. The slope. For each unit that is increase of x is approximately an increase or a decrease of b units in y. So it's telling you how far it's either going up or down based upon x moving over 1 unit. The correlation coefficient, this is the direction, the strength of and the linearness of an association between x and y. If it's not a very big number, like this is not a very big number, that 0.11, negative 0.11, it's a negative relationship, and it's not a very big number, it's a very weak relationship. And that weak relationship tells you that probably not a good measure for it. Okay, let's move on. If you looked at the ages in months and heights, and the heights in inches of 7 children, they're given here. So this is the ages in months, and this is their height down here. And they're asking you to find the least squared regression line. Interpret the slope and the correlation coefficient in the context of the problem. I got a cough. So let's do that. Let's come up here and press Stat. And let's go over to Edit and hit Enter. And let's go up to L1 and clear. I don't want to see this data in there. Thank you. Go up to L1, hit clear, data gone. Thank you. I'm going to move my mouse over just a little bit so I can key this data in quickly. And I've got 16, 24, 42, 60, 75, 102, and 120. And 24, oops. Need to move over to the other variable there, Charles. Okay, try again. 24, 30, 35, 40, 48, 56, and 60. Okay, so we've got that data in here. So I'm now going to do a stat. I'm going to go over to calculate, and I'm going to press number 8 to do the linear regression, or the least square regression, L1, L2, and I do a calculate on it, and I get this information. A is 20, 20.40, 20.4. B is 0.34, and my R is 0.999. So it looks like it is a really, really, really strong correlation. That 0.99, that means it's a strong positive correlation. My B is 0.34. That tells me that for every month, they're putting on 3/10 of a pound. Okay? I'm sorry, 3/10 of an inch. That's what that would be telling me. And it's telling me that the 0, okay, when x is equal to 0, babies are born at about 20.4 inches. Well, I think most babies are, right around that 20.4. That's, what is that, 20 inches and nearly 20 inches, or I'm sorry, 20.4 inches. Golly, I can't even get the words out of my mouth today. Okay? So, strong positive linear relationship between age and the height of the children. For each increase in age of 1 month, there's approximately an increase of 0.34 inches in height of the children. Okay? The ages in months given here predict the height of a child who is 4.5 years old. Well, let's go back to our data here. How could we do this? Well, one of the things I'm going to do is I'm going to repeat that calculation. Stat calc 8. Okay, I'm not changing anything there, but I'm going to actually store the data in a variable. I'm pressing vars, yvars, and I'm going to save it as y1. And then I'm going to come down here and calculate it. Why did I save that data in y1? Because now when I press y equals, it's stored in here as y1, and I can do a second graph. And it will actually graph that data out for me. Okay? Once again, zoom 9. There it goes. And there's the line being drawn in there. So if I want to look at what it's going to be at a particular value, I can do a second calculate. It's this one here. And I can calculate at a certain value, 1 at 4.5. And it will actually calculate the value of y. Oops, gotta be on the right thing. Excuse me. It was being picky with me. Okay. See, it's on the number there. It needs to be on the line. Okay, second trace. Okay, I want to calculate the value of 4.5. Enter. It says it's invalid. What am I doing wrong? Oh, wait a second. 4.5 years old is going to be 4 times 12. That's 48. And 6 more months would be 52 months. Got to be predicting the right value here. Okay? At 52 months. Okay? And it gave it to me. At 52 months, it is 38.19. We're basically 38 inches high. Okay? Okay, it says now predict the height of someone who is 20 years old. Okay? Well, we could do that too. 20 times 12 is 120. 240. So basically what I could do is I could come down here and press second trace value of 240 and hit enter. And am I doing something wrong here? Am I on the line again? Don't want to be on that one. I want to be on the line. There, I'm on the line now. Okay. Second trace value 240. it's not doing it. Wonder why. Okay, let me just go back and look at that equation again. It was 20.4 plus 0.34x. Well, we could actually put that in right here and say that it was going to be 20.4 plus 0.34 times, let's see here, 20 times 12 is 240, and 240 times 0.34 plus 20.4 gives me 102 inches. That's 8.5 feet tall. Do we know anyone who's 8.5 feet tall? Not playing on my basketball team. I wish there were. So what happened here? Why isn't it working? Okay, if they're 4.5, I did get it to predict something there. Well, let's see here. 4 times 12 is 48 plus that's 54 months, right? That would be 20.4 plus 0.34 times 54. And we did get a number there, right? 0.34 times 54. 0.34, 54. Thank you. Plus 20.4. That's 38.76. 38.38. Yeah, 39 inches. That's approximately 3 feet. So at 4.5 years old, they're approximately 3 feet high. I could buy that one. Why is this one so outrageous? Well, you know what? This is called extrapolation. And anytime you're doing extrapolation, the least squared resistance line should not be used to predict y values outside of the data set. You don't need to predict something that's beyond where your data set ends. So if you look at our data here, our biggest number is 120. We really should never do anything above 120. And this 20 years old is about twice what it needs to be. So therefore, we're getting a number that really doesn't fit. And that line would not be a good predictor of what's going to be happening in the future. It is unknown whether the pattern observed in the scatter plot continues outside of this range. This is a situation that in geometry we talked to you about called inductive reasoning. Inductive reasoning works as long as everything's going to continue on in the same way. Where it doesn't work is when it quits doing that. And we all know that our heights don't continue growing like we do when we're babies. We quit growing higher, taller, at some point in our lives. And that's why this is a good example of how extrapolation can get you into trouble and can get in the wrong information. So the ages and months and heights of the 7 children given gave us this line right here. Okay, this equation can be used to estimate the age of a child who is 50 inches tall. They're saying, what happens if you calculate the linear regression going the other way, L2 versus L1? The heights, can that actually tell you about how old a child is? You do. You get a little equation like this one here. Is this helpful? Well, you know, you've seen this equation used in the CSI shows when they're measuring the height of a person and they come back and say, we can predict how old someone was. Basically, they can use this linear regression going backwards, and they can get a predictor of how old a child was based upon its height. Even though we don't get the same least squared resistance line here. We don't get the same line here, do we? but it's an interesting concept. Okay? If we're trying to predict x from y, we'll use this line. If we're trying to predict y from x, we would use this line going forward. Question. What about the mean and of both the x and the y's? So the mean of the x values here and the mean of the y values here will always be a point on that least square regression line. It will be there on it, okay? And you can use that as a kind of a pivot point to try to see if the line works and if you twisted it a little bit, okay? The correlation coefficient and the LSR are both non-resistant measures. That means they don't change a whole lot, okay? There are some formulas on the formula chart. If you look at this one, y hat is equal to b0 plus b1 x. Well, b1, that's the slope, and b0, that's the y-intercept. You can actually find the b1 by taking the summation of every x value minus the mean and every y value minus its mean divided by the x value minus its mean squared. This will give you this b1 value. What is this? Rise over run. That's all it is. Okay? But b0, you can find that by taking the y hat, the y bar, the mean, and taking the b1 value you might have already calculated, and the x mean, and you'll find this b1, or this b0. Another way to find the b1, take the standard deviation of your y values, standard deviation of your x values, divide them, and multiply it times r, and it'll give you b1. Let's try that just for a second. We got some statistics, if you do the 5-number statistics, on the speed limit and the average number of accidents. We've got x bar, y bar, sx, yx, and r. Can we find some of these values? Well, I'm going to use this one right here. R sy divided by sx. We're going to find b1. Okay, so I'm going to get my pencil here. Okay, I've got my pencil. I'm going to take r times s sub y divided by s sub x, and that's going to be equal to b1. So let's just plug those values into a calculator. 8.4 divided by 11.6 times 0.9981. And what do I get? I get 0.7227. Well, that's 0.73. So my B1 value here is 0.723. Do you see how I used this calculation here and these values right here? Why would this be important? You know what? I've seen this on the AP test where they would give you some statistics of some data that they calculated and ask you to find the least squared resistant line. But they're not giving you the data, they're just giving you these statistics. Oh, so we might have to go back and use these formulas. They're testing you a little bit there. Well, now that I've got the B1, I can use the X bar and the Y bar to find the B0, right? So B0 is going to be equal to Y bar, 18, minus, it was B1, wasn't it? Yes, it was B1. It was calculated right here. 0.723 times X bar, which was 40. So if I key that into my calculator, 18 minus 0.723 times 40, and I get negative 10.92. So there's my B1, there's my B0, and that's exactly what I've got right down here for my X sub hat. Okay? So using this information, Predict the number of accidents at 50 miles an hour. Well, I can take the 0.723 times 50 minus 10.92, and I wind up at 25.23 accidents. That was my predictor. Cool. I hope you guys are seeing how this works. If you have questions, I would encourage you to come to the Toga session and let's work through a couple of these and see if we can't figure out how they work. Okay? In the class Connect this week, I will try to go over some of this information again, and I will see you there. Bye.